Stripping down science. The Naked Scientists.
Well, hello, it is Sunday the 19th of December. Welcome to The Naked Scientists with me, Chris Smith.
And with me, Dr. Kat Arney.
And I'm Dave Ansell.
It's our Christmas special this week, and we've got some festive treats in store for you, including finding out whether it's worth asking Father Christmas for a fancy carbon fibre-based bike, or if an old-fashioned steel one is just as good. Kat.
And we'll also find out what festive food and drink combos are best for avoiding dyspepsia, better known as indigestion.
And I've got a fantastic science trick you can use to impress everyone at your Christmas party. I'll show you how you can blow out candles round corners.
Sounds intriguing, thank you, Dave. And also on the subject of the festive period, open your drinks cabinet and grab your cocktail shaker.
So what it was to take sodium alginate and calcium chloride, add a flavor and mix it with the alginate, and then drop it into the calcium chloride bath and form these little spheres. So one of the things you could do with these little spheres is put them in a glass of champagne and they'd move up and down like a lava lamp.
And yes, they are edible. That's molecular mixologist Darcy O'Neill, and he'll be telling us about the chemistry that you can bring to the cocktail bar. If you've got any questions for us, we would love to hear from you. You can, of course, contact us through Twitter. You tweet at Naked Scientists. You can write on our Facebook page. That's thenakedscientist.com/Facebook to get there. Or you can just drop us an email. It's chris@thenakedscientist.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientists with Chris Smith, with Kat Arney and with Dave Ansell. And first up, let's take a look at some of this week's biggest science breakthroughs. Kat, what have you got for us?
This is from the Christmas edition of the British Medical Journal, which is a wonderful source of slightly silly science stories as sensible researchers around the world just cut loose and go crazy, as we'll hear later as well. In this edition, there's a great paper from researchers in Switzerland and Germany, which is the traditional home of fondue. That's the tasty treat, mostly made up of a bucket of melted cheese. I love it. But while fondue is a tasty treat, eating such a large amount of melted cheese can cause indigestion, also known as dyspepsia. Now, traditionally, fondue is eaten along with hot tea, which is thought to prevent indigestion, but other people favour alcohol in the form of wine or even schnapps. Now, scientists wanted to find out which drink did go best with fondue and caused least indigestion. So they persuaded 20 volunteers to eat fondue and gave them either white wine, black tea, followed by either water or schnapps. And obviously, because this was a scientific experiment and not just a meal with their mates, they also added a small amount of a harmless tracer chemical. And by measuring the amount of tracer in the volunteers' breath, the scientists could work out how fast the fondue was leaving their stomachs. And they also measured the amount of alcohol on their breath and asked the volunteers to rate their feelings of indigestion, bloating and nausea during the experiment. And so the team actually found that alcohol did slow down the rate of stomach emptying compared to tea, and that adding schnapps also slowed it down further. So the combination of wine and schnapps apparently made people feel much fuller for longer. And this is a phenomenon referred to by the researchers as having a cheese baby, which people may be familiar with. But in fact,
not personally.
You clearly have not eaten enough fondue, Chris, in your life. But actually, the type of drink, whether it was wine or tea, made no difference to whether someone was likely to get indigestion or not. Now, even if you're not having fondue for your Christmas dinner, the scientists do think their findings may extend to the consumption of alcohol with other types of rich meals, such as the traditional British Christmas dinner. And I'm sure that myself and the Naked Scientist team will be conducting very rigorous experiments in this area over the coming weeks.
So the bottom line is, don't have copious quantities of alcohol with your Christmas dinner. Is anyone going to follow that seriously?
No.
No, didn't think so. Thank you, Kat. Dave?
Considering the weather, I've got a nice story here. Now, scientists appear to have found what looks like an ice volcano on Titan. Titan's a fascinating world. It's about as large as the planet Mercury. It orbits Saturn, and because the sunlight reaching it is so weak, its surface temperature is about minus 189 degrees centigrade. Now, despite this, it's got an active weather system with lakes and rivers and rain. But this isn't with water, it's with liquid methane and ethane. They've actually sent a probe down there and you can see lots of rounded pebbles on the surface and mountains. They're not made out of rock, they're made out of ice. So this is this strangely complete low-temperature analogy of Earth.
So what's a volcano doing there then?
Exactly. Randy Kirk and colleagues have found a volcano about 1 kilometre high on the surface of Titan. They called it Sotra, but rather than made out of rock, it's made out of ice. So the centre of Titan is obviously a bit warmer, possibly heated by gravitational effects from Saturn. Some of the water inside there is occasionally melting and it's spewing it up. And there's what looks like a whole series of kind of lava outflows coming out to one side of it, and it's kind of flowing down, make these beautiful sort of shapes coming off it.
So the thing that makes this happen is because Saturn is huge and exerts a very strong gravitational effect, and Titan's quite close, it gets squeezed and stretched as it goes around Saturn because it's not going around a perfect circle around the planet, and that tidal stretching and squeezing makes some friction inside the moon, which melts some water and presumably drives this volcanic effect.
Yeah, that will be certainly one of the effects warming up Titan. And this obviously makes Titan even more interesting to study, as there's all sorts of more exciting geology going on, but with a completely different set of materials to Earth. But also, of course, wherever there's molten water, the chemistry gets very interesting, and there's always the kind of possibility of there being something to do with life involved.
So Darwin's warm little pool, but somewhere over there, millions of miles away.
And rather a lot colder, yes.
Thank you, Dave. Now, can you get drunk by immersing a part of your body in alcohol? Well, that was vaguely the hypothesis that a festive team of doctors from Hillerød Hospital in Denmark decided to investigate. And Dr. Christian Hansen joins me to tell us what they did. Hello, Christian.
Hello.
Well, they say that Heineken refreshes the parts that other beers fail to reach. What were you trying to do?
Well, in Denmark we have an urban myth that alcohol can pass through your feet if you submerge them in alcohol, vodka mainly. So we thought that was quite an important study to do because it's never been shown that alcohol can pass through your skin. There's been done some studies with the cadavers and that didn't really show anything in particular. So
it's hard to tell whether someone who's dead is drunk though, isn't it?
Exactly.
So what did you do?
Well, we bought some of the cheapest vodka we could get our hands on, and we sat down for 3 hours, submerging our feet in this vodka at the hospital.
When you say submerging your feet, do you mean as in when you have those stereotypical pictures of someone with a cold and they sit there in an armchair with their feet in a bowl of hot water and a towel wrapped around their head? Is that what you were sort of doing? You had your feet immersed in a bowl of vodka?
Yeah, except for the towel, that would probably be a fairly good image of what we did. And we had the lab examine our blood for ethanol for the 3 hours, the duration of the experiment.
So blood samples were taken regularly during the experiment to determine what the concentration of alcohol was in the bloodstream at any point? Exactly,
every 30 minutes. And they're, of course, rushed to the lab to make sure that the ethanol concentration didn't reach lethal levels.
And how many of you were participating in the study?
3 of us, and we were all employed at the hospital, so we had no students or volunteers in the experiment.
Okay, did you find any alcohol getting into the bloodstream?
None at all. At first we thought quite confident and happy, almost intoxicated, but we actually measured if we had any spontaneous hux occur and stated our self-confidence level, but it didn't really show any significant changes.
So in other words, as well as measuring the level of ethanol in the bloodstream, you were also doing subjective measures of whether you were experiencing inebriation, Dutch courage, or in this case Danish courage, and speaking too much, speaking loudly, that kind of thing. And everyone had that, but they didn't actually register any alcohol.
No, it didn't.
Did anyone get tempted to drink the alcohol after the study when people's feet had been in it?
Yeah, it was kind of difficult because we didn't really know what to do with the alcohol. It should be disinfected and no bacteria should be present, so it was quite difficult putting it in the toilet afterwards. So it was quite a shame, but the study was effectful, I'd say.
So talking seriously for a minute, the implication is that you can't actually absorb alcohol in any way, shape or form, at least at the level of detection of your assay. In other words, how sensitive the lab's test is, which is probably pretty good. And so this suggests that people actually are going to have to take alcohol through their mouth or potentially through other routes in order to get it into the body, but definitely not through the skin. Yes,
I'd say through the mouth would probably be the golden standard. But we've only measured vodka with 38.5% of alcohol. So there should be experiments done with stronger alcohol, I'd say.
So maybe onto the Calvados next year then?
Yes, probably.
Christian, thank you very much.
You're welcome.
Good to have you with us. That's Christian Hansen from Hillerød Hospital in Denmark, and you can actually find the paper where they describe doing that experiment in the December edition of the British Medical Journal. Kat.
Seems to be lots of food and drink stories. I've got another food and drink story here. And in case you were thinking of shunning turkey for Christmas dinner this year, not chowing down on a fondue, but on hamburgers, researchers from the University of Arizona have some advice that could help to reduce the formation of potentially cancer-causing chemicals and also inactivate food poisoning bugs in grilled meat. Now, when you pop your burger on the barbecue or under the grill in this weather, it goes nice and brown and crispy, but at the same time, chemical reactions that take place as the meat is heated up produce chemicals called heterocyclic amines. Now, these chemicals are thought to be partly responsible for the increased risk of cancer in people who eat a lot of cooked meat. Cooking meat at a lower temperature can reduce the formation of the chemicals, but it also increases the chances that bugs like E. coli, which can cause food poisoning, won't get destroyed. Now, researchers at the University of Arizona have suggested that a chemical compound called carvacrol, found in the herb oregano, could actually help to solve both problems. Now, carvacrol's an antioxidant, one of these things we hear so much about, and an awful lot is said about them, some of it not really very relevant, but the scientists think that it might reduce the formation of these heterocyclic amines as the meat is cooked. And, as an added bonus, the compound also has antibacterial properties and can inactivate bugs like E. coli. And the scientists, led by Sadhana Ravishankar, are currently testing a range of plant compounds mixed with hamburgers to try and find the most effective combination that still tastes nice, because apparently the carvacrol itself, it doesn't taste that great, so a little more work needs to be done. But this idea, maybe you could have a sort of a multi-purpose burger with some flavouring and this antiseptic anti-cancer agent in it. Intriguing.
Burger à la Dettol. No, that's what I was going to say, that surely this is only any good if people actually like oregano or whatever this other carvacrol tastes like. So it's got sort of limited use. Is there no way that chemists can tweak the molecule a bit to come up with one that doesn't have a vile taste or impart too much of a flavour but still has the beneficial effect?
Well, I think that's what they're trying to do, testing various compounds to get the acceptability of taste with actual functional benefits. And some of the problems with doing this kind of research, testing plant compounds, is sometimes you do have to have an awful lot of the plant compound to get a benefit from it. So, for example, there's a lot said about red wine, this chemical in red wine called resveratrol that can have cancer-fighting properties. But to get enough from red wine, you'd have to drink about 100 bottles a day. And Chris, I don't think even you could manage that.
I was going to say, last time I went for a drink with you, Kat, you were well on your way there.
Lies, all lies.
Now, does owning a lightweight carbon fibre bike cut down your commuting time? Well, that was the question that Dr. Jeremy Groves, who's a consultant anaesthetist at Chesterfield Royal Hospital in the UK, was asking, because he tells in a paper that's published for Christmas in the British Medical Journal that for many years he was driving to work, and then he went on a fitness drive by deciding to actually commute the 43.5 kilometres to work and home every day. And he decided to do it on a steel-framed bike that he bought for 50 quid second-hand after sprucing it up a bit. That's how he puts it in the paper. But the thing was that he realised it was taking him quite a while to do this journey, so he wondered whether investing in, thanks to the government's Cycle to Work tax incentive scheme, it was worth investing in a nice expensive carbon fibre lightweight bicycle in order to shave some time off of the commute. Would this work? So to find out, he decided to do a trial on himself. So what he did was to buy a £1,000 carbon fibre 9.5 kilo weight bicycle, which he then compared with his old steel 50 quid 13.5 kilo steel frame bicycle. And each day he tossed a £1 coin to decide which bike he was going to use, and then rode the journey using a cycle computer to keep a track on how long the journey was taking and what speeds he was achieving. And he did this for 6 months. He did 26 trips on the carbon fibre bike, and he did 30 journeys on the steel-framed bike. It wasn't a blind trial, of course. He didn't blindfold himself. He knew which bike he was riding, so there might be a little bit of bias there. But here's the interesting thing. He clocked up 1,144 kilometres in travelling distance over the course of the trial, and when he averaged out the journey times on both different types of bike, the steel-frame bike took an average of 1 hour, 47 minutes and 48 seconds of cycling to do the round trip to work and back at the hospital. And the carbon fibre, very expensive, 50 times more costly lightweight bike, he took an average of 1 hour, 48 minutes and 21 seconds. He does point out that the travel times are longer in winter because you're more frightened of falling off on your carbon fibre bike because the wheels are much narrower, so it's harder to keep your balance. He also points out that cold weather means that you tend to ride more cautiously, you might wear more clothing, which weighs you down a bit. But the point is that although the carbon fibre bike weighs 30% less than the steel frame bike, actually, when you take into account the person plus the bike, the number is actually only 4%. In other words, your weight plus the bike's weight, the bike only contributes 4% difference to the combined weight. And since you're therefore the sole determinant of the weight you're moving, largely, it means that you should, as he points out, pay more attention to the weight of the cyclist than to the bicycle. And he concludes his paper by saying a new lightweight bicycle may have many attractions, but if the bicycle is used to commute, a reduction in the weight of the cyclist rather than that of the bicycle may deliver a greater benefit and at much reduced cost. So there you go. If you're riding to work, trusty old steel frame bike that's donkey's years old and will probably go on forever is probably the way to go. It is, of course, an N of 1 study, so be careful, interpret with caution. Dave, you ride everywhere.
Yeah, and my bike is certainly a very ancient steel frame bike, which has gone through various different iterations, although I do manage to keep breaking the frame. But anyway, I saw an interesting story about the sun, which appears to be varying in ways which no one expected. The sun is obviously incredibly important for the Earth. It provides virtually all the energy to drive the climate and, of course, life itself. I've been studying the sun for a long time, but almost all those studies have been done from the ground, so we have a very limited information on how the output of the sun changes in frequencies which don't make it through the atmosphere. These are particularly important for the upper atmosphere because if they're being blocked by the atmosphere, all that energy is getting dumped into the upper atmosphere, so they heat it up. And up until now, atmospheric modellers have assumed that the sun output changes through the 11-year cycle, but all different wavelengths change together. But a NASA satellite called SOURCE, the Solar Radiation and Climate Experiment, has been studying these changes in the sun since 2003. And it's found that all the wavelengths are not the same, not equivalent. The amount of ultraviolet light seems to vary 10 times as much as the average, and the infrared varies much less than you'd expect. This could explain why people have noticed that the temperature of the stratosphere varies far more than you'd expect during the solar cycle, because you have an 11-year solar cycle where you have lots of sunspots and the sun's hot. Other places you have not many sunspots and the sun's cooler. And the extra UV you're getting when the sun's very active should be heating the upper atmosphere, and so it's doing this.
So can I just clarify one thing for a second? So what you're saying is that the sun has this 11-year cycle, or sunspot cycle, when it goes through periods of lower activity, peaking, and then it comes off again. And the wavelengths of different types of light coming from the sun vary over that 11-year cycle, so they vary as well, but they don't all vary by the same amount.
That's right. The shorter wavelengths are varying more than the longer ones. And this is obviously going to feed into climate models and things like that. And the initial ideas are that the sun probably has less of an effect on the climate than we'd previously assumed, just because of the way everything feeds back into itself. And so quite possibly these variations in the sun have had less effect on the climate in the last 100 years than people think. There's
a study that got done a few years back where they were logging the level of water and tide marks going back about 100 years in some of the lakes in Africa, including Lake Tanganyika. And they were able to see 11-year cyclical peaks in the flooding, arguing that the sun was driving rainfall on the Earth in line with the solar activity, and this was what was causing these rises and falls in the lake level.
Yeah, I mean, the sun, even minute changes in the sun's output are going to have effects, especially in certain areas on the Earth, because the climate is just so chaotic.
But maybe not as large, what you're saying is maybe not as large as we previously anticipated.
Yeah, I mean, although this is very, very preliminary.
Thank you, Dave. Well, if you'd like to read a bit more about any of the items we've covered this week, the references and the transcripts of each of those news stories are online now at our website, nakedscientist.com/news.
Keeping you abreast of the world's best science. The Naked Scientists.
Well, Merry Christmas. You're listening to the Naked Scientists Christmas festive special with me, Chris Smith, and with Kat Harney, and with Dave Ansell.
Coming up, you've heard of the 12 Days of Christmas. Now meet the ocean equivalent. We've got a selection from the 12 marine critters of Christmas, including unusual fish with a built-in invisible searchlight.
And shaken, not stirred. Is there any chemical basis behind James Bond's particular penchant for the way that he likes his martinis? The chemistry of cocktails is on the way.
I can't wait for that. But first, it is time for this week's episode of Planet Earth. Now, it's been a sub-zero this week in the UK, so we're taking you to one of the hottest places on Earth, the Afar Depression, and that's a region of the Sahara Desert on the Ethiopian border. But it also contains a series of rifts that are slowly ripping the African continent apart to form a new ocean. And that's what makes it a dream destination for geologists like Oxford University's Dr. David Ferguson, who explained to Sue Nelson the Afar Depression's appeal.
Well, Afar is geologically is a fascinating place because it's one of the few places on the Earth's surface where we can see the continental crust, and that's the rocky outer shell of the Earth that we live on. We can see it being ripped apart by the movement of tectonic plates, and hot magma from the Earth's mantle, which is the region below the crust, wells up to fill the gap and creates a new ocean basin.
How long have geologists known about this particular region?
So the first geologists to visit Afar were probably there during the 1960s and the 1970s, and it was recognised at this point that it was an exceptional place to understand how plate tectonics work. Unfortunately, due to the independence war between Eritrea and Ethiopia, we haven't really been able to visit the area for decades. So it's only in the last 10 years or so that scientists have been able to get back into Afar and been able to study in detail the processes that are going on there.
Before we go into the processes themselves, you've brought a couple of rocks here. Describe to me and to us what this surface, this area of this rocky, remote place looks like.
So in this bag we have a piece of basaltic lava. This is it's one of the most common rocks on Earth, actually, and this is one of the newest rocks on Earth. This is just approaching its first birthday. So this piece of their surface was underground a year ago. And
it's almost like a hard, black-grey piece of sponge, very
so it's
porous.
full of holes, so these are all the gas bubbles that escaped. It's quite spiky because it flowed across the surface, and it's still young enough to preserve all these spiky bits. And if you look carefully, you can see it's full of shiny crystals, large white, kind of glassy-looking crystals.
Oh, yes.
And these grew underground in a magma chamber where this lava was stored before it erupted. We have another piece of rock here, which is very different. There's no bubbles in this, and this is a piece of volcanic
very
glass.
Shiny.
It's incredibly shiny.
Almost looks like black marble.
Yep, it's very heavy, and it's composed almost just entirely of glass.
Let me just feel a bit. It's like the size of a bag of sugar, this bit, and actually feels pretty much probably a bit heavier than a bag of sugar as well.
And the difference between these two really is their chemistry. And this magma was so viscous that the crystals that we see in this lava weren't able to grow, and so it's just solidified into just a chunk of glass, really.
Now, this great big rift, you say it's an ocean-forming rift. Does that mean in the foreseeable future that the area, this part of Ethiopia that you're looking at, will be covered in sea in, I don't know, hundreds of thousands of years' time?
Yes, the crust that forms Ethiopia is being slowly stretched apart at about 20 millimetres a year, for instance. However, right now in Afar, that process within the last 5 years has speeded up dramatically, and it's moved approximately a metre a year or 2 metres a year even within the last 5 years. We think this probably goes in stops and starts. And so at the average speed of maybe 20 millimetres a year, if this continues for 10 million years, for instance, then we would probably see a new ocean basin in Afar.
How normal is this for a geologist to actually see this taking place?
It's incredible. It's pretty much a once-in-a-lifetime opportunity. Tectonic plates move very slowly, and it's not common that we get a chance to witness a kind of furious stage of activity. One other well-documented phase, which was in Iceland in the 1970s. But apart from that, this is a very rare occurrence. And we think in this part of Afar, it probably happens every 400 to 500 years.
So how often do you get to go out there? Because I know from reading, you kept a blog at one stage that you had this hot date with a volcano. So how likely are you to go out there? Or do you go out there as soon as you hear that there's activity? Is it like being like a fireman on call, or the geologist equivalent of a fireman?
Yeah, a little bit. We're volcanologists on call. We go out for two reasons. We go out to collect rock samples from older lava flows to perform experiments on. But yes, as you say, when we hear that there's an eruption, we try and get out there as quick as we can because we want to collect samples and we want to actually witness these eruptions in progress if we can, to learn a little bit about it. We're always ready to drop everything and run out if we get the opportunity.
And that was on-call volcanologist David Ferguson talking to Sue Nelson. You can download the latest Planet Earth podcast as well as find links to Planet Earth online on our website. That's thenakedscientist.com/Planet Earth.
Lifting the lab coat on the world's best science. The Naked Scientists.
You're listening to The Naked Scientists Christmas special with Chris Smith, with Kat Arney and with Dave Ansell. If you have any science questions for us, you can, of course, tweet at Naked Scientists, which is what Radium Yttrium has done, and is wondering, Kat, what is your favourite holiday season cocktail recommendation?
Well, I'm a sophisticated lady, so I do like a classic champagne cocktail, Angostura bitters, brandy, sugar cube, champagne, or a brandy sour, sort of brandy, sugar and lemon juice. I like that.
A margarita all the way. I just cannot get enough of it. I love, well, and obviously until you fall over and pass out. But yeah, margarita, my top one. Dave, what's your recommendation?
Can't say I've ever acquired the taste. Orange juice is nice.
Orange juice and water. There you go, that's Dave's cocktail combination. OK, Ellie Liverzage says, my boiler is broken, it's very cold, I've got a heater I can use, but where's the best place in my house to put it? My husband thinks downstairs as heat rises. We were just talking about this, me and Dave, and our take on it is, well, it depends what you actually want to do, because it's not as simple as saying, well, we just want to heat the house. Because, yes, heat rises by convection, and convection currents will carry the warm air upstairs in your house. So if you want to warm upstairs, it's actually better to just take the fire upstairs and warm your bedroom if you're going in there. If you want to be downstairs and have the downstairs part of the house warm, put the fire downstairs and close the doors off so that you're just heating the room that you're in. That's probably the most effective way to do it. If you want to heat the whole house, then open the doors, put the fire downstairs, and what will happen is that the warm air will flow up through the corridors and things to the upstairs, displacing down the cold air, which will fall because it's more dense down to the ground, get heated up, and it will all circulate around the house. And given enough time in a more powerful fire, you could heat the whole house, assuming that the fire can put enough energy in to outcompete the cold, which is basically coming in through drafts and the heat that you're losing through the roof and so on, because your house is radiating energy. Now, talking of very cold things, Dave, here's a very good question from Matt in Norwich, and he says, listening to the story of Titan, is it possible to gain energy from the cold in that volcano you were talking about?
That is a very interesting question. You can't gain energy directly from cold, but what you can do is get a lot of energy by moving heat from somewhere which is warm to somewhere which is cold. And that's what essentially a steam engine does, or a car engine. Any of the heat engines work exactly like that. However, the efficiency, the colder that you get that cold end of the system, the more efficient the process is. So if that cold end was absolute zero, then if you move a kilojoule of energy from something warm to there, then you'll get a kilojoule of useful work out. If it's hotter than that, it gets a lot less. So whilst you can't get energy from cold directly, you can get a lot of energy by transferring heat to somewhere very cold.
And we were talking about precisely that thing on the show the other day, because we were talking about storing energy as the difference between a very hot thing and a very cold thing, which is actually a local group who were doing that.
Yeah, the isentropic and the cold, that's the reason why they're keeping the cold end very cold. It just increases the efficiency of the whole process.
Cheers, Dave. Now, it is our festive Christmas Naked Scientists, and I absolutely love cocktails. We were debating about what our favourite ones are earlier. I'm a margarita person. But what's actually going on, chemically speaking, inside that cocktail shaker? Well, to find out, I got together with the University of Western Ontario's chemist and cocktail connoisseur, Darcy O'Neill.
Well, early on, I studied chemistry, and then I ended up working at a refinery for 6 years. And then I decided to move on to a different city and didn't find anything that was really working for me career-wise, so I decided to do some bartending. And then I ended up back at the University of Western Ontario. Then I decided to take the science and apply it to the drinks that I was making.
How did that go down with the customers?
Went down really well. I was surprised at how well people, usually you'd think people just come out for a drink. But once they started understanding how the drinks were made and then bringing in some science to it, they really, really took to it.
Was it relatively easy to start to dig into the chemistry of cocktails? Did you actually find that it was pretty easy to, from a chemist's point of view, understand what was going on? Or is there still just a black art to cocktail making, and that shaken, not stirred, is very much on the lips of the consumer, but there isn't much science behind it?
Well, getting early on, I was probably one of the first dozen people to actually look at science in cocktails. So there was a lot of, low-hanging fruit to work with. So even just talking about ice, why things cool down, how they cool down, talking about how certain things mix. I mean, that was pretty simple early on. Now it's actually getting more difficult because you're always trying to find new material or new and interesting facts that people want to hear.
Give us some examples.
Well, let's see. Right now we are doing essential oils. There's been this perception that they're artificial flavors, which they're not. They're just distilled oils. So much like ethanol, you distill off the ethanol, but if you're to continue distilling grape brandy, for let's say, you'd end up with cognac oil, which comes off at about 110 Celsius. It's not artificial, but it's a very, very potent flavor compound that you can make a champagne-flavored non-alcoholic beverage. So trying to get people to understand, the distillation process and all this background stuff that gets more complicated as we go along.
But the interesting thing is that we're now in a position where someone like you, who has a lot of chemistry knowledge behind you, can take your knowledge and explain what we're already doing. But could we turn the equation round and start saying, right, based on what we know about chemistry, we could start doing something very unusual to make a whole new type of drink or cocktail or combination or gustatory experience?
That's actually starting to happen. It's following after molecular gastronomy, which is the science in food. And what they've called it now is molecular mixology. And it's taking science and doing something with a cocktail to create something completely unique. And one of the most interesting ones, or early ones that really got a lot of media attention, was caviar. It's not really fish eggs, but they look like fish eggs. So what it was they take sodium alginate and calcium chloride and make a calcium chloride bath, add a flavor and mix it with the alginate, and then drop it into the calcium chloride bath and form these little spheres. One of the things you could do with these little spheres is put them in a glass of champagne and they'd move up and down like a lava lamp. People were quite fascinated by it.
I remember using that same trick to make immobilized enzymes in a chemistry class at school, but I never thought of putting them in champagne.
Yeah, and it's funny, a lot of that's where all of this stuff's coming from, is that, a lot of people, it's surprising, have a high level of education, but enjoy food's a passion, drinks are a passion, and so a lot of people bring or cross the information over.
Now, one of my favourite characters historically is James Bond, for all kinds of reasons, but is there any science behind his shaken not stirred claims?
Yeah, actually, last year at Tales of a Cocktail in New Orleans, which is a kind of a conference for high-end bartenders and industry people, they looked at, the science of shaking, because you've always heard shaken or stirred, or, which one is better and which one produces a different drink. So they actually did a test. They took a cocktail shaker and put in a thermocouple, put different amounts of ice. They weighed the ice, and then they'd shake them and see what would happen. And what they figured out is that for shaking a drink, if you shake it 20 times for approximately 20 seconds, that's as cold as it's going to get, which is about -7 Celsius. And then they found with stirring, it takes a lot longer to bring the drink down to that temperature. So probably twice as much time, 40 seconds, to get it to that plateau, because it actually doesn't really go any colder than -7.
There was a company that were claiming that their ice was the best ice for cocktail making, wasn't there?
Yeah.
So that basically blows them out of the water.
Well, it does. I mean, there's still good ice and bad ice. Obviously ice picks up a lot of flavors, so using clean, fresh ice is always the best idea. There's no such thing as the perfect ice for a cocktail. Any ice will do.
What about if you used dry ice? I don't mean that in a funny way, but that would presumably lower the temperature much further.
Definitely, but what happens is that it also carbonates the drink. You'll taste the acidity in it. So for a lot of people who do Halloween-type drinks, they'd like to put the dry ice in it and make it froth and stuff. But if you've ever tasted it afterwards, it tastes much different.
You've tried that, have you?
Yeah, oh yeah. Working in a lab, there's always something I can try. So bring home dry ice and give it a shot.
One of the other things that I heard one person saying with the shaken not stirred business is that when you make a cocktail, some of the things mix quite well with stirring, but there are other heavier things that don't. And actually shaking the cocktail up does make a very big difference to the way in which the combinations of chemicals mix round, and therefore the flavour sensation they impart to your tongue and your mouth will differ between shaking and stirring.
Well, the funny thing is, one of the studies was done at the university I work at, and it was about bruising gin. So what they found was that it really doesn't change much, but I think the oxidation potential goes up or something like that. And it was a very slight difference, but never let facts get in the way of a good story, because that's what part of drinking is. You know, you go to a bar and you want to talk about things. If you're a little bit too matter of fact, it becomes no fun to talk about it.
I could not conclude an interview with an expert on the chemistry of cocktails and I suppose mixology without asking you, what is your favourite tipple?
I'd have to say the Manhattan. If you go to a bar, usually you'll get it right. It's not a drink that you can mess up too much. Usually it's about 2 ounces of whiskey. Now, not Scotch whiskey, but American whiskey or Canadian whiskey is the general preference. Half an ounce or to an ounce of sweet vermouth and a dash of bitters. Angostura bitters works amazingly well. And just basically stirred as opposed to shaken. And then garnish with a maraschino cherry.
And served?
In a cocktail glass, or similar to a martini glass. I actually have a Manhattan glass, which is a little bit shorter.
So you've got to have the right kit. It's very important that a chemist has got the right glassware, isn't it?
Absolutely. Glassware is something I've got a little bit too much of. It's kind of a collection. This glass has to have everything right, or this drink has to have the right glass.
So none of those funky plastic tumblers like Dr. Kat's fond of when she goes out drinking. Just joking, Kat. That was cocktail chemist Darcy O'Neill talking to me from the University of Western Ontario about his work as a molecular mixologist. Now, it is our Christmas special, so let's take a seasonal dip into the underwater world. Helen Scales has been busy choosing the 12 marine critters of Christmas, and here are just 3 of them to get you in a festive mood.
As a marine biologist, I think there's no better place to get in the festive mood than among the weird and wonderful creatures of the ocean. So, instead of partridges in pear trees, I've been diving beneath the waves to track down the 12 marine critters of Christmas. And here are 3 of my favourites. First up is a denizen of the deep that comes complete with its own set of fairy lights.
I've seen many, many weird and wonderful fish, but one of my favourites is a thing called the stoplight loosejaw, which is a deep-sea fish, and it has some very unusual abilities. It's, like many of the fish that live at depths like that, is capable of producing light. It has 2 different lights on its head, one behind its eye and one a bit further down its jaw. And one of these is blue, which is not unusual. A lot of the fish and other organisms at that depth use blue light because it travels quite far through the water. But the really unusual thing about the stoplight loosejaw is it also has a red light, and it's one of only 3 kinds of fish that can do this. Hardly anything else can see it. Everything's eyes are tuned to blue light, so the red light that's produced by the stoplight loosejaw is pretty much invisible, so it has its own private wavelength of light. We're still not totally sure what it uses it for. It could use it as a torch to sort of shine ahead of it as it's sort of swimming around looking for prey, or it could even use it to communicate with other stoplight loosejaws, and of course everything else would be oblivious.
James McLean there from the Natural History Museum in London with a fish that glows just as brightly as Rudolph's nose. For my second critter of Christmas, let's swim out into the big blue to catch up with an ocean drifter that's just about perfect for this time of year.
So sea angels are a group of snails. They're not too distant relatives of garden snails that you would find on land in your backyard. They are very beautiful animals. You know, they have these transparent bodies and these giant wings. They look a lot like angels. But one of the really interesting things is that in Antarctic waters, Clyone antarctica has developed this evolutionary tactic to sort of make up for the fact that it doesn't have a shell. These sea angels have lost that protective ability, but instead they've evolved, or at least Clyone antarctica has evolved, bad-tasting compounds that it synthesizes. So fish and other predators learn very quickly when they take a bite of Clyone that it's not something that they want for a meal. This has led to actually a very curious interaction between sea angels and a totally unrelated group of animals, the Hyperiid amphipods. They're sort of distant cousins of shrimp and of krill. And these amphipods have learned that if they grab onto a Clyone and essentially hold it hostage and swim around carrying this giant sea angel on its back, fish and other predators won't eat the amphipod because it's got this bad-tasting Clyone carried along with it.
How crafty is that? Rob Jennings there from the University of Massachusetts, introducing us to the beautiful sea angels. Now let's meet an organism for which one set of sex organs just isn't enough.
The chimeras are probably what I would describe as the forgotten cousin of the shark and ray. Chimera in Greek mythology actually means a creature that's created from other bits of animals, which when you look at a chimera, you can actually sort of believe that. While chimera is a sort of a group term for these fish, within that there's individual species that are known as rabbitfish, ratfish, elephantfish. So there's a range of different names for different chimera species. When you get to the head end, that's kind of where it gets really interesting, because sharks, rays and chimeras all use electrosense to detect their prey. And the chimeras have some very unusual modifications of their snout. I still sort of have trouble sort of imagining the mechanics of this, but the males actually have a retractable sex organ on their head. They have traditional sex organs as well, but they seem to have this other one as well. And to my knowledge, I don't know if anyone's actually seen it in use, but it is something that sort of slightly boggles my mind.
A classic example of sex on the brain. That was Matt Gollock from the Zoological Society of London.
Helen Scales there with 3 festive marine critters. You've got to love those sea angels, which make themselves unappetising by swimming around with another animal hanging on to them, which doesn't taste very nice.
Well, I was going to make some kind of joke about you see enough at the office Christmas party of men who seem to have sex organs on their heads, and I'm not sure that 5 Stoplight Loose Jaws is going to be taking over in any Christmas songs very soon.
I like the way you sung it, though.
Yeah.
But anyway, if you want to find out a bit more about the rest of Helen's picks as the 12 marine critters of Christmas, you can actually find them on a special edition of The Naked Scientists, which is called the Naked Oceans Podcast, and you can actually find that at nakedscientist.com/oceans.
Now, it's time for our kitchen science, and we're doing outside broadcast today, live. We've sent Dave to meet up with Ben Valsler, who is outside in the car park, because this experiment involves a naked flame and a bottle of wine. Ben, what are you up to?
Well, I'm sure lots and lots of people will have been to exciting office parties with candlelit dinners and that sort of thing, and we wanted to try and recreate that atmosphere, but obviously we can't go lighting fires in studios. People will get very upset about that. So we're in the somewhat less romantic situation of actually sitting in the boot of Dave's car. Now, fortunately, he's got an estate, so we're not too cramped, but it's still not the most glamorous location for an experiment. Hi, Dave, how are you doing back there?
I'm just about okay. My legs are going to sleep slightly, but otherwise fine.
So what experiment have we got? It's related to something we'll see at an office party.
That's right. I thought we'd do an experiment on candles, so I'll light my candle here, eventually.
And this is, of course, why we're in the back of a car. If we were to do this outside, the candle would probably go out straight away. So we've got a candle lit. It's nice and steady. Now what are we doing?
Well, basically, we're doing an experiment on blowing out candles.
That doesn't really sound like much of an experiment. Blowing out candles is something that pretty much everybody can do. What's so special about it?
Okay, well, first of all, the way a candle works is you've got molten wax, it wicks up the candle, then evaporates, and then it burns once it's evaporated. So when you blow it out, you blow lots of air across the candle, you cool down the wick a bit, you blow the flame away from the wick, it stops evaporating anymore, and it goes out.
And it's not actually the wick that's supposed to burn, is it? In fact, the wick, ideally, will stay pristine, and it's just the vaporised wax that we're burning.
That's right. So I thought we'd do an experiment on blowing candles out from behind things.
From behind something. So this would be if you can't quite get to the candle, maybe there's a present in the way or some flowers or a bottle of wine or something, but you still need to blow the candle out.
That's right, and see what kind of things you can still blow the candle out for.
Okay, well, let's get that lit again. It's starting to get quite smoky in Dave's car now. If you hear a very loud bang and then we go silent, then just call the fire brigade for us. So what are we going to blow it out past first?
Well, I thought we'd try a box. So I've got essentially a very small present here. It's actually the box of matches because it's convenient. And if I put that next to the candle and blow...
Well, it hasn't worked. And in fact, oddly, the flames seem to go towards your box of matches, which doesn't sound very safe, but you were blowing in the opposite direction.
That's right. Because the box has got sharp corners, the air hits it, it gets deflected sideways. When it hits the corner, it will carry on going in a straight line. What's called the boundary layer gets detached, and it goes off away sideways. It doesn't go anywhere near the candle. You get a bit of air kind of swirling backwards, a bit of a vortex, which just moves the flame very gently.
So that's where it's coming towards us. It was actually this turbulent vortex coming off the edge rather than the intentional direction of your breath.
That's right. So don't try blowing out candles from behind your presence. It won't work.
So anything square, anything with sharp corners, you won't be able to blow the candle out behind.
Certainly very sharp corners. But then I've got a wine bottle here.
Excellent. So we're going to crack open a bottle of wine. And, I see. So we've put it right next to the candle. It's actually very, very close to the candle, which I guess you're doing to try and warm up your red wine, get it ready to drink.
In here would be a good idea, but just to try and block the candle completely. And now if I blow from behind that, I'll put essentially my nose onto the bottle of wine and blow.
Oh, well, that time it went out straight away. But this bottle is almost as wide as your box of matches, so surely it will deflect the air just as much.
Well, the strange thing about fluid dynamics is that if you get a stream of air and it hits a surface, it tends to stick to that surface as long as that surface doesn't curve too much. So the smoothly curving bottle, the air will tend to stick to the surface of the bottle, bend all the way around, get back to the candle, and the candle blows out.
So where we had corners before, which caused the stream of air to break up, to become turbulent, it's actually flowing round the round bottle because of this lack of corners. It's sticking to the bottle, and that actually means that it pulls it all the way round to the candle and blows the candle out. Excellent. Where else do we see this sort of thing in action?
Well, this is the reason why wings are smoothly curved rather than with sharp corners in them, because a wing is designed to smoothly change direction of the air, so it sticks to the surface, it bends around a corner, so the wing pushes the air downwards, so the air pushes the wing upwards, and the plane flies.
So blowing out a candle on the other side of a bottle actually shows you how aeroplanes work.
Part of it, certainly.
Well, if that's something you want to try and show off at your office party with, it's a dead easy experiment to do, and we're going to get Dave back into the studio, and I really need to warm up and repair this crick in my neck. So, Chris, back to you.
Thank you very much, Ben and Dave. So demonstrate that at your office party and you'll wow everyone else out, assuming that is that you haven't set fire to the table.
Distilling the best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
Right, you're listening to The Naked Scientists with Chris Smith, with Dave Ansell and with Kat Arney. And Kat, here's one which is probably better if you answer, because if I say anything remotely sexist, I know I will be blown up, probably in one of Dave's experiments. H-Town Insomniac MR says on Twitter, why do babies calm down when you put them? Now, when I first read this, I thought it said in a washing machine. It says on a washing machine. Does the inside of a pregnant woman sound like a washing machine?
Not to the best of my knowledge, though I have never been pregnant. And Chris, surely you would never make a sexist remark. But yes, I think that there is definitely some truth in this, because obviously the inside of a lady is not a very quiet and still place. People walk around, you're sort of constantly talking, joggling about, wandering around, all that kind of stuff. And so I should think that the vibrations of a washing machine and perhaps a bit of the noise would help to calm a baby down. A friend of mine always used to swear by sticking the kids just in the back of the car and driving around until it fell asleep. So I'm sure there's probably some truth in that, and it probably is the vibration that does it.
Terrific, Kat. Thank you. Dave, you've brought the cold in here with you. I can feel the cold oozing off of you. So ideally, here is Clive. He's in Chelmsford, and he's got a question for you which is right up your street. Clive, hi.
Hi. Yes, why is snowflakes different sizes and shapes?
Snow is made up in the atmosphere. It's basically when water vapour goes directly from a vapour to a solid to straight to ice. It's sublimed into ice. And there are lots of different ways it can do this. There are lots of different modes of growth. There are some modes which produce long, straight crystals and make the crystals get longer and thinner. Some cause them to branch in different ways. Sometimes you can get you can get plates forming. Sometimes you get long, straight needles. And this, as the temperature and the humidity changes. So if a snowflake moves around in a cloud, both the temperature and the humidity will change while it's growing. And so depending exactly how long it stays in one temperature and one humidity, then another temperature, another humidity, you'll get different forms of growth. So the snowflakes which are produced will be slightly different. They don't necessarily all have to be completely different, but there'll be lots and lots of different types.
Thank you, Dave. Silfa Zoidberg got in touch and said on Twitter, @NakedScientists, if you'd like to have a go at that, what happens to all the salt that goes on the road in winter? Well, the answer is, Silfa, that actually when the ice melts, the salt gets washed to the margin of the road. Lots of it ends up in storm drains, so that ends up ultimately going to the sea, so that doesn't really matter. But on country lanes and things, and in residential areas, lots of that salt actually gets washed to the side of the road and then ends up in your garden. And there is a problem with salt contamination of soil, because the salt does make the soil become very, very saline over time, especially on busy roads that get very large amounts of salt dumped on them, and this can actually have a problem for the wildlife, chiefly plants and things like that. Now, we've heard from Alan in Norfolk, who says, earlier on I was listening to what you were saying about sunspots. Do sunspots have anything to do with the Earth's magnetic field? The answer is, Alan, that sunspots are an independent entity which occur on the sun, and the Earth's magnetic field doesn't make them happen, but they can interact with the Earth's magnetic field, because thanks to the fact that we have a magnetic field, life is possible on Earth, because the sun is continuously giving rise to what's called the solar wind, which is a 1,000,000-mile-an-hour maelstrom of charged particles that go whizzing past the Earth and are deflected around the planet by our magnetic field. And in fact, it's the interaction of those charged particles with the magnetic field that gives rise to phenomena such as the Northern Lights, the Aurora Borealis, and down in the Southern Hemisphere, the Aurora Australis. But there was one very, very important event that was documented in the 1850s. It was actually in 1859 and is known as the Carrington event, in honour of the British astronomer Richard Carrington, who first saw this. And what he spotted from his amateur observatory in the south of England was an enormous sunspot on the 1st of September 1859. And this coincided with a very dramatic event that happened on Earth, when observers worldwide recorded the sky turning blood red. There were bolts of lightning shooting down from the clouds, like St Elmo's fire, for example, and telegraph operators all over the world in countries that had the telegraph were getting electric shocks, people were being killed, and there were fires being started by all this current surging down the telegraph connections. What was happening is that this sunspot was associated with an enormous coronal mass ejection, and this is where the surface of the sun launches a huge amount of charged material as a plasma out into space, going very, very fast with very high energy. And this would have impacted on the Earth, and this impact of these charged particles going into the Earth's atmosphere and inducing electricity to flow in anything that could carry a current was what gave rise to the event. And the colour in the sky was because of the charged particles interacting with the atmosphere and with the Earth's magnetic field. So the sunspots do have an impact on what we see here on Earth, but they're not directly linked to the Earth's magnetic field. The Earth's magnetic field will interact with what they do and produce the events that we see. Now, on the subject of good quality questions, it's that part of the show where we go for our question of the week. And standing in for Diana O'Carroll this week is Dr. Kat Arney. Kat.
Yes, I have important news for anyone eager to ensure at their Christmas party that the camera sees their best side.
Hello, my name's Shane, and I've got a question. My question is, why is it that some people are very, very photogenic, while other people are not quite as easy on the eye, to put it politely? Thank you very much.
So why is it that even the prettiest people like me come out badly on film, while some ugly mugs like Chris seem to get away with it?
So I'm Fiona Moore, and I'm a lecturer in psychology at the University of Abertay, Dundee. I think the thing about being photogenic is that you could be the best-looking person in the world and just take a terrible photograph. But there are certain things people can do to make themselves more or less photogenic, but there are certain things that some people just are lucky enough to have, which means that they'll take a good photo. And I think that's got a lot to do with maybe bone structure and probably as well being able to smile naturally and look natural in front of a camera, which doesn't seem to be something that everybody can do, which I know from personal experience. The kinds of things that people can do to make themselves look more photogenic are things like, for example, I read a study recently where the camera angle can make people look more or less attractive depending on whether they're male or female. So a camera angle tilted looking down on a female face makes her look more feminine and therefore more attractive, whereas a camera angle sort of looking up at a male face makes them look more masculine. There are things that women do, obviously, like wearing makeup, which it tends to give you a healthier appearance, and we know that a healthy appearance is very closely related to attractiveness. So things like having a healthy skin colour and skin texture things like having sort of blood perfusion in the skin. So someone that exercises regularly, has a lot of blood circulation, makes them look healthier. And evidence recently from the Perception Lab at St Andrews shows that these things are related to diet you eat. If you've got lots of fruit and vegetables in your diet, you've got better skin colour and you look healthier and therefore more attractive. So there are things that people can do to enhance how photogenic they are, but I think ultimately it comes down to how naturally people behave in front of the camera and perhaps very basic things like bone structure.
So the combination of genes, good health, cosmetics and the skill of the photographer, but what makes a face attractive in the first place?
There are things like having a symmetrical face, so not having too much asymmetry in the two halves of the face tends to be associated with attractiveness, and I suppose that's just good luck and good genes. We know that women with feminine facial features are considered much more attractive, so that's things like having bigger eyes and a smaller jaw. In men, it seems to be more complicated. Having sort of a feminine male face is attractive, and so is having a masculine male face. So I think a lot of it is down to your good genes.
So if you've got the perfect face for radio, like the Naked Scientist team, it's probably better to remain behind the mic than in front of the camera. Now, next time, from a feast of faces to a diet of milk.
Hi, this is Budi Prastia from Seattle, Washington. I have a question. Are humans the only animals to consume the milk of a different species? Thank you.
So what do you think? Get in touch by email, chris@thenakedscientist.com. Write your thoughts on our forum at thenakedscientist.com/forum.
Kat, thank you very much. Kat Arney with this week's Question of the Week. And if you have any questions you would like us to tackle, then do send them in to chris@thenakedscientist.com. Well, that's all we've got time for this week, and in fact, that's all we've got time for in 2010. This is our last show of the year. We'll be returning on Sunday the 9th of January, live to air, and in the podcasts on subsequent Tuesdays. And the first thing we'll be looking at when we return next year in 2011 will be the subject of medical dissection and how medical students are taught anatomy in medical school. We'll be looking at a new documentary from New Zealand with the guy who made it, Paul Trotman, who'll be here in the studio to introduce us to how he filmed people who were going to leave their body to medical science and then spoke to the students who dissected those people. We'll also take a visit to Cambridge University's own dissection room to find out actually what students take away from the whole process and how effective it is at actually helping people to learn their anatomy to turn them into good doctors. Also, thank you very much to our wonderful Naked Scientist team, without whom none of this would be possible. So thank you, Ben, Dave, Kat, Sarah, Mira and Diana. And of course to you for listening as well. Now, we have got a little Christmas present for you because we've got a new strand launching called the Naked Science Scrapbook, which promises to draw out the facts. And a special sneak preview of that we'll publish on our main Naked Scientist feed on Christmas Day, so you'll be able to get that, but it will also be in iTunes, and you can look it up there. It's called Naked Science Scrapbook, and you can subscribe to its feed there. In the meantime, have a very Merry Christmas. Thank you once again for joining us for a whole year of The Naked Scientists in 2010, and we look forward to having your company in 2011 when we celebrate the 10th birthday of The Naked Scientists. Until then, goodbye.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at nakedscientists.com.